Welcome back, nerds. So we are working on Descartes' rule of sign still, like I was saying before I started the video. And I know that, I was kind of being chased by the bell yesterday. I was trying to finish this before, the bell got me. So I just want to make sure that we're all clear on how Descartes' rule of sign works and what it's used for and when it's useful and things like that. The best analogy that I was able to give period one earlier today was like a very specialized tool, right? Most of you at home, there's probably a junk drawer or a toolbox in the garage somewhere. There's probably a hammer somewhere in your household, right? And you feel like, yeah, hammers, those are good for driving nails. And you're right, they are. But the thing is I don't know if you know this, but there's like dozens of different kinds of hammers. And I don't mean even size. I mean different kinds of hammers, right? And there are some hammers that are so specialized, you might only use them once a year, if that. Like I could tell you, I have never once needed to use a dead blow hammer. I know what they're useful for. I know when I might need to use one, but the situation has never arisen, which is a good thing because I don't own one. A dead blow hammer, in case you don't know, is a hammer that in the head of it. Imagine this is the head of the hammer. It's got a bunch of like BBs or sand, or it's got weight inside it that can shift around. And it's called dead blow because when you hit something, it wants to bounce, right? Hammers are metal unless you get a wooden mallet or something like that, but they'll bounce a lot of times. Well, there's a lot of applications where you need your hammer to not bounce when it hits whatever it hits. So if you fill the head of it with weight that can shift around, when it strikes whatever it's trying to hit, rather than bouncing, all the movable crap inside it absorbs that impact and it just wiggles around. So it's a highly specialized tool that is used every now and then. Descartes' rule of sign is like that. It's really only used every now and then. I mean, how many test questions am I going to give you on it? I'm going to make you use it one time on the test. And if you choose to never use it after that, I wouldn't be surprised. I mean, last night, because I am a colossal nerd, I was doing math for fun. I stayed up an hour later than I should have, literally doing math for fun. There was a math competition on campus yesterday called Math Aces, and I wanted to see what the students were up against. And this was one of the questions that I did late last night. And the job was to figure out what all the solutions were and then add up the biggest and the smallest solution. Well, off to the side here, this was me actually, where's my work? I have it over here. I brought it with me so I could have it in the video. Here's my work for that question. The first thing I did was my P over Q test, like I taught you to do. So I found all the positive and negative factors of 12. I listed them out. Luckily, the front number, which would have been Q, was 1. So they were all just these numbers over 1. And this is 12 numbers. Do you see that? This is 12 numbers. And when I looked at my options, they were all pretty. So I knew that the solutions I was finding needed to be pretty. So it was helpful that it was multiple choice. So I knew I was looking for pretty solutions. These are the only possible pretty solutions. So you know what I did? Rather than guess and check my way through all 12 of them, I used Descartes' rule of sign. And I was so thrilled that it was actually useful for once. And I really do say for once, because other than teaching it to my students and showing them like purposeful examples of when they might want to use it, I've never once needed to use it. But because I was challenging myself to go as fast as possible, I said, okay, let's see what's up with Descartes' rule of sign. And I counted the sign changes in f of x. The sign changes in f of x would have told me the number of possible, positive, real solutions. There was one sign change. So what that did was it guaranteed to me that my graph had one positive x-intercept. So what that means is, even though there was 6 of them here, only one of them could work. The very first thing I did was plugged in positive 1. This is me plugging in positive 1 using my remainder theorem. and I got 1 plus 3 minus 3 minus 9 minus 4 minus 12, and I saw that that wasn't going to get me 0 because these are the only two positives. So the moment I saw it wasn't going to get me 0, I stopped working. Then I plugged in positive 2, and I saw that gets me 0. I then did synthetic division with it and got to this 4th degree polynomial. But here's what's up. The moment I knew that positive 2 worked, I was instantly able to discount, meaning forget about positive 3, positive 4, positive 6, and positive 12. I knew they couldn't work. It was impossible because Descartes' rule of sign told me there was only one positive solution, and I had already found it. And that's all Descartes' rule of sign does. It literally goes, hey, let's just throw out some of the options for you so you have less things to check. That's all it does. But when you're on a time crunch, like a competition or a test, that is when it becomes useful because it gets rid of solutions for you, possible solutions. So you can stop looking at them. I was so happy, I think I smiled, that I was actually able to utilize Descartes' rule of sign rather than just show it to students. It actually came in handy for me. And it made me very happy because, like I said, big nerd here, okay? So we're going to start by doing another Descartes rule of sign question. But before we do, I just wanted to recap this one and what we did. We took our original f of x, which could be thought of as being f of positive x, and we counted up how many sign changes that we saw. And the only time that my terms oscillated positive, negative, or negative, positive was right there. It went from a positive number to a negative number. So it happened one time. That guarantees me that I have one positive real solution. It's a guarantee. And why is it guaranteed? Because complex numbers always come in pairs. That number says there are 4 solutions because it's a power of 4. So this one positive, it couldn't have been 0 positive because there was more than 0 sign changes, but there wasn't more than 1, and I can't subtract 2 from this 1. If I try to subtract 2 from this 1, because remember I told you what you decrease by even numbers. If you try to subtract 2 from this 1, you get a negative 1. And this is telling you the number of real solutions. If I said, hey to you, if I said, hey, in my wallet, I have negative $3. You'd kind of look at me like I was crazy, wouldn't you? Because how do you have negative 3 of an object? Oh, I got negative 1 apples. What? So to say you have negative 1 solutions, what? That doesn't make any sense. And that's why we don't try to subtract 2 from this, because we can't. It would tell us we had a negative number of solutions. That's just ridiculous. So then what do? Then we check negative x, f of negative x. The long way of doing it is plugging in a negative x everywhere and then cleaning it up. The fast way of doing that is anytime you had an even exponent, it's not going to change. But every time you have an odd exponent, it'll get a different symbol. That's the fast way of doing it. Then I counted my sign switches. There's 1, there's 1, there's 1. That is 3 sign switches. That means I could have had 3 negative real solutions. So along with that 1 positive real solution, that got me all 4 of my solutions, which means there would have been no complexes. But Mr. M, what if there wasn't 3 negative real solutions? Then I go, okay, all right, that's a possibility. But if there's not 3 of them, I have to discount that number by 2 or a multiple of 2. But why? Because the complex answers are always going to come in conjugate pairs. So if there's less than 3, then there's 2 then there's 2 less than 3, which makes 1 a possibility. But if there's 1 positive and 1 negative, that's only 2 solutions. And I know there's 4 of them. So the other 2 must have been complex. Okay? Last night's homework had a typo on it, and I mentioned it at the beginning of class before I started the recording. Hopefully everybody corrected it. But there was supposed to be an exponent of 2 right here. Right? Okay. The first thing you should have done was factored off the x squared. We never attempt to do Descartes' rule of sign if our GCF includes an x. How come? Because when your GCF includes an x, what do we know is automatically an answer, guys? If your GCF includes an x, what is automatically an answer? 0. The problem with that is 0 is neither positive nor negative. So it kind of goofs up Descartes' rule of sign. All right? So what you should do is, well, actually, it goofs up P over Q. It might not goof up Descartes' rule of sign. Now that I've said that. It definitely messes up P over Q. Regardless, you factor off the x squared, and you get an x squared minus 6x plus 9. Now, I know that you know how to solve quadratics, but I just wanted to demonstrate how Descartes' rule of sign can be used. Would I have used it on a quadratic? Freaking no. But I'm just showing you. If you count your sign switches, there's 1 and there's 2. So you could have 2 positive, bless you, 2 positive real solutions or no positive real solutions. And then if you plug in negative x, what you would have gotten is this wouldn't have changed. This would have. And this is that. And there are no sign switches. So there are 0 negatives. We know a quadratic has 2 solutions, right? So then, if there are 2 reals that are positive, how many complexes would this have had? No, this one right here. None. Yeah, don't worry about this. We already know what that is. I'm just looking at this quadratic right now. Of course, if this quadratic had no positive and this quadratic had no negative, it obviously had 2 complex. And I'm pretty sure that when you did your work, if you use the quadratic formula because, oh no, this factors. This factors, doesn't it? You ended up with 2 positive real solutions. I think they're both 3, right? I think this is x minus 3 quantity squared. But if you felt the need to use Descartes' rule of sign, it confirms to you that, yeah, you were either going to have 2 pretty positive answers, or no, excuse me, 2 positive answers, or you were going to have 2 complex answers because quadratic formula dictated a plus or minus. So should you have done that? Oh my God, no. But I'm showing you could. It could be useful. Okay? So let's do it again. New example. We have x to the 5th. How many solutions am I on the hunt for then? 5 solutions. Because it's a degree 5, I know I have 5 solutions. Let's look at f of positive x. It's literally just the equation that I already have. And I am going to take the time to rewrite it because these are for, good notes. Do I expect you to rewrite it when you're doing your work? Nah. I mean, why would you, right? Just count the sign switches in f of x. Let's see. Here's one. And here's one. And there's one. Oh my golly. And there's one. That's 4 sign switches on the positive. There could be 4 positive real solutions. Or there could be less. There could be less. But if there's less, you have to decrease that number by 2 because what you're saying is there might have been complex answers. And complex answers always come in pairs. So I subtract 2 to allow for 2 complex answers. Or, I could have had absolutely no positive real solutions. Because again, I could have allowed for 2 more complex solutions. Now let's see what the negative case tells us, and that is figuring out what f of negative x is. I'm going to show the work of me plugging in a negative x at all the x's, but I'm going to be real, I never do that on my own when I'm doing the work. What I do instead is I see anything with an odd exponent, and I just put the opposite symbol in front of it. Anything with an even exponent would stay the same. But this is what it would look like. So like I said, this had an odd exponent. So that means now it's negative. But this had an even exponent. So putting in a negative x changed nothing for that term. This is an odd exponent. So now this is going to be a negative number here, which cancels this negative, and now it says plus 5x to the third. So symbol switched. Even exponent on a negative cancels it out, so that term was unaffected. But odd exponent, that is going to change the symbol, plus 8. I would love it if you could skip this line for yourselves and just go directly to this line. If you can't, that's fine, but I would like you to be able to, just so you're doing less work. I'm not a fan of doing extra work when it wasn't necessary. I am a fan of putting in the hard work when you need to. I'm big on hard work, but this is just a realization thing, so that'd be great. Now let's count the sign switches. Negative to negative, no. Negative to positive, here's one. Positive, 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 positive. Oh, hey, there's only one. That guarantees that this graph crosses through the x-axis one time on the negative side. There is, Descartes' rule of sign is telling me, there is a negative real answer. There may or may not be positive real answers. We're not sure. And the only way to be certain is either graph it or factor it and solve for x. But I know for a fact that I have a negative answer. But we know that there's 5 solutions. That means we need to figure out how many complexes there could have been. How many complexes in that situation? None, because 4 and 1 already add up to 5. How many complexes in that situation? 2. And in the last one, 4. So there are 3 options for us. Our graph is going to behave like one of these 3. And just to remind you from what I told you yesterday, complex solutions create wiggles in our graph. So if you were curious to know what this graph looks like, I actually have it on Desmos. And it's unfortunate that I can't get Desmos on the camera, but everybody in the room can see it. And right here, the part that I'm circling, that's the wiggle that I'm talking about. This actually ended up being this situation, where there was one positive, one negative, because the graph only crosses the x-axis twice. And these 2 complex solutions, again, you can't see it in the video, but you guys in the room can see it, created this little wiggly thing right here. So complex solutions create wiggles in the graph, but the wiggles don't interact with the x-axis. That's what that means. Cool beans? All right. I don't have an image of this one. I didn't even bother graphing it because I didn't feel like wasting the time on it, because someone else in first period, rather than me graphing on a Desmos like a big nerd, asked an amazing question, and I want to make sure that that question makes its way into the video. But I'm curious to know if any of you have the same questions. I want to ask. Any questions out there? Anything I can help? Yeah, Hunter, what's up? Columns. Okay, so why are there options like this? So the reason why is because we're not guaranteed that there's 4 positive. Are you comfortable that if there's less than 4 positive, that means I've said there's some complex? You Comfortable with that? Okay, but the complex have to come in pairs, right? So if I had to subtract 2 from that to get to here. But I'm also not guaranteed to have 2 positive real solutions. Because this number is 2 or more, I could have still had more complex solutions. So your job is to continue to subtract 2 until you're not allowed to because you'd get a negative number or you'd get a 0. Okay? So it just creates all the options. For example, let's just say I was really, really mean and found there was 5 sign switches somewhere. Then you would say that's 5 or 3 or 1 because you're decreasing it by 2 until you can't anymore. Okay? All right. Gavin? So if there's a missing term, Descartes' rule of sign doesn't care. Descartes' rule of sign doesn't care if you have missing terms. And the reason why is because a missing term would be a 0, right? Like you would hold it, let's see, 5, 4, 3, 2. Okay, this one wasn't missing anything. 4, 3, 2, neither was the one before it. But let's just say this was missing. How many x to the 4ths would I have had? 0 of them. So it wouldn't matter if you said plus 0 of them or minus 0 of them, because 0 doesn't have symbol. So Descartes' rule of sign doesn't care one bit if there's a term missing. Nope. You only need placeholders for divisions. Long division and synthetic division. And never for Descartes' rule of sign, never for P over Q, never for the remainder theorem. Nope. Okay?
Why does it go from least to greatest for the complex, but greatest to least on the other ones?
Well, the reason why we're going to go from so complex is always just the leftovers. And that's typically going to make it go from smallest to greatest. Typically. Does it always happen? No. But it's because let's just say you don't want complex solutions. So you're hoping there's 0 of them. Or you're hoping there's not a lot of them. Because if there's a lot of them, you can't graph very well. Like the thing that I just showed you on Desmos, I literally would not have been able to tell you where the wiggle in that graph was. Because all I knew was that there was complex solutions that are possible. That told me there was a wiggle somewhere. But without plotting a billion points, I never would have known where it was. So you're actually hoping to minimize the number of complex if your ultimate goal is to graph. Like what would this graph look like? No flippin' clue. I think 4 complex solutions, all I know is that this graph has a couple wiggles in it that don't touch the x-axis, if this is the graph. So I have no clue what it looks like. And so that would be nearly impossible to graph unless I just felt like plugging in hundreds of x values. Any more? No? Okay, well then I'll just offer it up. How many of you have done question number 4 in the homework? 1 person, 2 people, 3 people, 4 people, a handful of you. Did you find all 4 options like I said? She did. How? Well, actually, where's the homework page? Here it is. It says there's 4 combinations, right? When you did Descartes' rule of sign, what you found was there was a situation where both the positive and the negative case you could subtract 2 from, right? And that's what created the extra situations. So let's envision a degree 7 polynomial and this is what the sign switches counted up to be. So I counted up all my sign switches on f of positive x. There was 4 of them. But you know that means it could have been or 2 of them or 0 of them, correct? And if there was 3 negatives, that means there could have been 3 or 1. This is 6 options. And here's why. 1, 2, 3, 4, 5, 6. And that's how you build out all of your options. So when they could both be more than one number, you have to find all the possible combinations. So if I listed all of these out, it would look like this. 4, 3, 4, 1, 2, 3, 2, 1, 0, 3, 0, 1, and then the complexes. So a minute ago, Max, you asked about the complexes always go from smallest to greatest, and I said they usually do, but not always, right? When you have a setup like this, where both numbers could be more than one number, then it will no longer do that. So if it's a degree 7 polynomial, we know that the column, the vertical, has to add to 7, right? So there would have been none of them here. But 4 plus 1 is 5. There'd be 2 of them here. I'm not sure what just happened to my brain. I said 2 and wrote 5. 2 plus 3 is 5 again. But 2 plus 1 is 3. 0 plus 3 is 3. And 0 plus 1 is 1. So it kind of went from greatest to least, or smallest to greatest, but that's only because I chose to write it in that order and I didn't have to. So you could have just written whatever order you want. The point is, when both the positive and the negative have more than one option for you, you have to build out the entire grid. And Addison, you figured that out like a boss. Good. How about you? No? It's okay. And I figured that would throw a lot of people for a loop. My plan was to show you something like this in the notes anyway. But that's how you would handle that. So when you do the one in the homework, I believe I said there's 4 combinations, right? So it looks like that. So what you end up doing is going this one and this one, as well as that one and that one. And that's how you get all 4 combinations. There would be, yes, 4 columns, yes. Like this one had 6 columns because there were 2 red, 2 blue, and 2 green. This one. Cool? Okay, you looked at me crazy when I said there was 6. No? Okay. 1, 2, 3, 4, 5, 6. Okay. All right. Questions on Descartes' rule of sign? How to use it? When to use it? No? I'm going to be real with you. I almost never use it. I teach it, and I teach my students when they could use it. But how often do I use it? I mean, not all that often. And last night is like the first time that I've ever, when I was doing that challenging question, thought, I wonder if Descartes' rule of sign will help me here. And it was only because I was trying to do the question quickly because it's a competition that was timed. The students were given 45 minutes to do as many of these questions as they could. There are 20 questions. I was able to do 8 of them in the 45 minutes. And I'm a nerd. So, yeah. Anyway, let's find all the zeros of this polynomial. Would I use Descartes' rule of sign on a question like this? I'm going to be real with you, I probably wouldn't. Why? Because it's a 3rd degree polynomial. It's really not that hard. 3rd degree polynomials are actually pretty easy to deal with. They only have 3 solutions. Descartes' rule of sign doesn't even start to flex its muscles until like 6 or 7 solutions. Anything before that, and I'm like, yeah, I mean, maybe I'll use it, but maybe not. I will, however, show you how it's true. I'll show you that it's true for this one, okay? So let's count our sign switches. This is a 3rd degree polynomial. We know we're dealing with 3 solutions. Sign switches, plus to plus, plus to plus, plus to minus, right there. Oh. There is 1 positive solution. Could I go ahead and do the whole, plugging in negative x stuff? I could. But I wouldn't normally. And here's why. this is a cubic. If I find one of its solutions, how many does it have left? You can say the obvious answer. It has 2 left, right? What kind of polynomials create 2 solutions? Quadratics. Which means if I can find one of its solutions and use synthetic division, my result will be a quadratic. And I can either factor that or solve it using the quadratic formula. Which means Descartes' rule of sign really doesn't have a use here. It's true still. And I know that I have a positive solution. At least I know that. Okay, then now what? What would I do after that? What I would do is I would immediately go to my P over Q test. Where P is all of the factors of 2 and Q is all of the factors of, well, 2 again. How about that? So P, the factors of 2 at the end, are plus or minus 1, plus or minus 2. And the bottom factors of 2 are 1 and 2. Technically, I should have said plus or minus 1, plus or minus 2 again, but that's kind of redundant. So what's the point? Now, we list out all the possibilities. Why am I listing out all the possibilities? Because I'm listing out all the numbers that I might need to check using the remainder theorem. Gives me plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 1 over 2. But if I do 2 over 2, that's 1 again, so there's no reason to do it. This is 6 options. 3 positive, 3 negative. So am I guaranteed that my positive solution is on this list? Actually, no, I'm not. This thing could do something wacky and have an ugly positive solution. Like 1 plus the square root of 3. So again, Descartes' rule of sign just guarantees me that one of my answers is positive. It doesn't even tell me that it's one of these pretty ones. You know what it does do though? If I find it's one of these pretty ones, I don't even have to think about the other positive ones because now they're not possible because there is only one. That's its only use. And because of that, I'm not even going to use it. Okay? So here's what we're going to do. We are now going to use our remainder theorem. And the remainder theorem is where we start literally guessing and checking options from P over Q. Remember how remainder theorem works. We evaluate at the 0 and hope we get a remainder of 0. Because if we do get a remainder of 0, we found a factor. And if we know a factor, we have a solution. What is the very easiest number to plug in for x? Well, 0, you're not wrong, but that's not an option. Which of these is the easiest thing to plug in? 1. I'm not going to lie to you. Every time I try to solve something like this, the very first thing I do is check to see if 1 is an answer. Because it's really easy to plug in. Because if x is 1, you just ignore all the x's and you only write the coefficients. Because it says 2 times 1, 5 times 1, 1, and minus 2. So let's see what happens when we plug in positive 1. Yes, I'm showing the work. But remember the one I showed you that I did last night on my own? That was me plugging in 1. I literally just wrote the coefficients. I saw that those two canceled and then really quickly saw there was no way I was getting a 0 and I walked away from it. And I went to the next one and I plugged in positive 2. Because I knew there was one positive, I only was checking the positives. But that's only because this thing was a 5th degree polynomial. This is a 3rd degree polynomial. So even if 1 doesn't work, I'm going to go to the next easiest number to plug in. What's the next easiest? No, it's not. And you know why 2 is not the next easiest? Big numbers. The next easiest is negative 1. Because anything with an even exponent stays the same. Anything with an odd exponent, it just changes the symbol in front of the number. I always check 1 and -1 first. Always. Because they're easy. Let's see what this gets me. Gets me 2 times 1 plus 5 times 1 plus 1 minus 2. I don't even care what this equals. All I care about is the fact that when those cancel out, this doesn't equal 0. Walking away. Did me no good. It's not a solution. Next. You see, who cares what it equals? The only number over here that makes me happy is 0. This isn't 0, stop thinking. The next easiest number to plug in is -1. But Mr. M, I thought you said there's a positive solution. Why aren't you checking 2? Here's why I'm not checking 2. What if it's not 2? Then what am I going to do? Check 1/2? I'm not trying to do 2 times 1/2 to the 3rd power plus 5 times 1/2 squared and play with common denominators. I never plug fractions in when I'm using the remainder theorem because it sucks. I don't want to. It's too much work. I just hope that all my fractional solutions will come out of the quadratic formula or something like that. Or factoring. I don't want to plug them in. They bite. So why plug in 2 when I could just plug in -1 and hope? Now look, if -1 doesn't work, then what do? Then I'll go to 2. And so that's how I do it. I climb the ladder. I go from smallest numbers to biggest numbers, and I always go positive, then negative, positive, then negative. That's how you should do it. And then pray to math God that you never have to plug in a fraction. I'm going to do you a solid. I will never give you a situation where you must check fractions with the remainder theorem for factoring purposes. I won't do that to you. Not for factoring purposes. Okay? Because it's mean, and even I wouldn't do it. But let's plug in -1 and see what happens. Yeah, I'm showing the work. Would I actually show the work if it was me, on my own paper? No, I wouldn't. Instead, what I would do is I would just look up here, and everywhere that I saw an odd exponent, I would put the opposite symbol in front of that number. Even exponent, leave that number alone. Odd exponent, no x's. And by the way, that's what you would have gotten if you had actually done all of this. But this is slow, but whatever. Hey, what do these add up to? 0? Woohoo! You know what that means? X equals -1 is a solution. That also tells me that x plus 1 is a factor. So if the question said factor, I have one of my factors. If the question says find all the solutions, find all the zeros, find all the roots, I have one of those as well. This thing only has 3. We found one of them. Life is good. That's always your goal. Get yourself down to 2 solutions, because that means you're dealing with a quadratic. And quadratics are easy. The goal is always get to a quadratic if you can. Now we do synthetic division. Because if I synthetically divide my cubic by this linear, I get the quadratic that I need. X to the 3, 2, 1, none. It has no gaps in it. So life is good for that at least. So 2, 5, 1, -2. We already know that our remainder will be 0. We already know that. We just saw that. And dropping this 2 down. Here we go. -1 times 2 is -2. Adding straight down gets me a 3. -1 times 3 gets me a -3. Adding straight down gets me a -2. -1 times -2 is +2. Adding straight down gets me the 0 I needed. And because this was a cubic, I know that this is a quadratic. Specifically this quadratic. And since I'm trying to find solutions, we can either solve this quadratic by factoring, if it factors, or we could do it using the quadratic formula, whichever one you're more comfortable with. I prefer to factor. And yes, there are two numbers that multiply to -4 that add to 3. Those numbers are 4 and -1, right? I'm reminding you how you can factor regular old quadratics by grouping. You figure out what the two numbers are and you split your middle into those two numbers, then group. This way we also get practice factoring by grouping. The GCF here was 2x, leaving behind an x plus 2. The GCF here is -1, leaving behind an x plus 2. And now we have all three of our factors. There's one, and there's one. But the directions were to solve for x. So what does x equal here? Come on, guys. Right here. What does x equal, guys? I want everybody talking to me. Thank you. X equals -2. For this one, maybe you set it equal to 0 to figure out what it equals. Add 1 to both sides, and then divide both sides by 2. 1/2. So our answers written in numeric order are -2, -1, and +1/2. By the way, how many positive real solutions did Descartes' rule of signs say I was going to have? 1. And look, I would have had to gone all the way to that fraction to see if it was one of the pretty ones. And I'm a nerd, but I am not that big of a nerd, to be real with you.